So now we're going to go over these problems on chirality. This first group of problems, we're trying to label any stereocenters as R and S. So starting with valine, valine has just one stereocenter located this carbon. In fact, if you look at structures of amino acids, you'll find that amino acids in general have one chiral carbon in them, being the carbon that has the amine, carboxylic acid, R group, and hydrogen. The only amino acid where that's not chiral is glycine. Now there are a couple of amino acids that the R group is also chiral, but for every amino acid other than glycine, the carbon I've indicated in yellow is going to be chiral. And even better for amino acids, it's really easy typically to figure out the stereochemistry. Nitrogen is higher priority than carbon or hydrogen. That hydrogen that's not drawn in is pointing back and is our fourth priority. And then a carbon attached to oxygen is always going to be higher priority than a carbon attached to other carbons. Since the lowest priority group is already pointing back, we can draw our arrow, it's counterclockwise, and so the chiral center in valine is S. Now with naproxen, the hydrogen that's not drawn in, which is of course our lowest priority, is pointing forward. Other than that, we have to determine the priority between three other carbons. We have the carboxylic acid to the left, the aromatic structure to the right, and the methyl pointing down. Now the methyl that's pointed down, that's attached only to hydrogens, whereas the other two carbons are attached to other carbons or oxygens. That means that methyl group is going to be the lower priority of the three carbons. For the other two carbons, this carbon here to the left is attached to oxygen, which makes it higher priority than this carbon, which is attached to other carbons. So now we just need to rotate this molecule so that our hydrogen is pointing back instead of forward. But there's actually a shortcut we can take here. And the shortcut is because the low priority points forward. Can't use this in any other situation. I'm going to draw an arrow from 1 to 2 to 3. And that goes clockwise, which would imply R. But because the low priority is pointing forward instead of back, we take the opposite. And so this structure has S stereochemistry. All right, for part C, we have a chiral center located right here. Bromine, higher atomic number than carbon, is highest priority. The other three groups here are all carbon. But we have a methyl, which means that's a carbon that's attached to just hydrogens. That's going to be lower priority than the other two carbon groups. Now the other two carbon groups are actually a little tricky here. The reason for that is that to the right, we have this carbon that has this huge rest of the molecule attached. But on the left, it's just a couple of carbons. So which one's higher priority? Well, we've got to look at them carefully. So if we start with this one that I've highlighted in green, what else is that carbon attached to? It's attached to another carbon plus two more hydrogens. Now what about this one in purple? It's attached to 2 additional carbons and 1 hydrogen. So we have a point of difference. And so even though this one to the left that I've highlighted in purple has many less groups attached to it, many less carbons attached to it, because at the first point of difference it has more carbons, it's higher priority. All right, our low priority group, the methyl group, it doesn't have to be a hydrogen as lowest priority. It can be anything. But because that lowest priority group is already pointed back, we don't have to rotate the molecule. We draw our arrow here, 1 to 2 to 3, and we have S. In part D, we actually have to account for 2 stereocenters. There's 2 chiral carbons in this molecule. The one with the isopropyl group and the one with the bromine. So we start with the one with the isopropyl group. Now, both of these are going to be straightforward in that the hydrogen is pointing back, and that hydrogen is lowest priority. So if we go up, we have a carbon attached to 2 carbons. To the left, we have a carbon attached to 1 carbon. But to the right, we have a carbon attached to a bromine. And so that, because of the bromine, is going to be the highest priority of the 3 carbon groups. Second will be the carbon attached to 2 carbons, and third, carbon attached to 1 carbon. Arrow goes counterclockwise, and so this stereocenter is S. Over here, the bromine is highest priority, second priority to the left, and third priority down here goes counterclockwise, and we also have S. All right, part E, we have threonine. Threonine has 2 stereocenters. One here and one here. So let's try that again. One here and one here. So the center on the left, oxygen is 1, carbon to the right because of the nitrogen is 2, and the methyl is 3. The hydrogen not drawn in is already pointing back. So we have R. On the right, the nitrogen is highest priority. To the left, we have a carbon with an oxygen and a carbon. But to the right, we have a carbon that's bonded 3 times to oxygen. So that'll be higher priority here. Goes counterclockwise, and we have S. Finally, in glucose here, glucose has 4 chiral centers. And we can go through the same thing for each one of those. Over here with the oxygen, oxygen is first priority. The double bond to oxygen is second. And we have 3 over here. That's R. At the next oxygen, first priority here. Second to the right and third over here is S. The next oxygen, first priority up at the top. Second to the right, third over here is R. And finally R again over here. All right, question 2, we're looking for a name for the molecule that's provided. And anytime we're doing naming, that also means that we need to account for stereochemistry. Before we can do that though, we have to find our parent chain. And our parent chain goes straight across here. And that's 8 carbons for octane. Now we've got to name our substituents, because we're going to start here because there's a substituent right on that first carbon. 2 of them, in fact. So carbon 1, we have a bromine. We also have this ring. So we'll get to cycloalkane nomenclature actually very, very soon. But when we have a ring, we treat it the same as an alkane. We just add the term cyclo in front of it. So this has 6 carbons. So it's, instead of hexyl, it's cyclohexyl. Then we've got a bunch of methyl groups. There's methyls at 4, 5, and 2 of them at 7. And 6 has an isopropyl. So now we just put them in alphabetical order. 1 bromo, 1 cyclohexyl, 6 isopropyl, and I'm going to run out of room here. 4, 5, 7, 7 tetramethyl octane. Are we done? Not yet. We still have to determine the stereochemistry of each of our chiral carbons. And those are located at 1, 5, and 6. So our first carbon, highest priority is the bromine, second is the ring, 3 is to the left, that's R. Over here at carbon 5 we have a methyl, which is going to be third priority because the hydrogen is fourth. To the left we have a carbon bonded to 2 carbons. To the right we have a carbon bonded to 2 carbons. So now we've got to go further. With those, we only have 1 more carbon bonded at either of these positions. But if we go one carbon further from the left, we've got a whole bunch of other carbons. That's going to make this 1 and this 2. So our arrow goes counterclockwise, but because the hydrogen in the low priority group is pointing forward, we take the opposite, which is R. Same thing happens at the other carbon, and we get 6s. And just so that we can see that, again, our lowest priority group, the hydrogen, points forward. To the left, we have a carbon bonded to 3 carbons. That's higher priority than to the right or down, where those carbons are bonded to 2 carbons. As we go further to the right, though, we have a carbon that's bonded to more carbons, whereas going down, we just have methyl groups. So 2 here, 3, arrow goes to the right, we take the opposite, is 6s. All right, question 3 here, and to be perfectly honest, everything in question 3 here is straight off of old exams. And so what I'm looking for you to identify here is what's the relationship between the two molecules that are given. So in part A, you can see we have 2 stereocenters, one here and one here. What have we done? We've reversed both stereocenters. And we know if we invert both stereocenters, that gives us enantiomers. Usually. Because if we look at part B, we can see that in part B, we've also inverted both stereocenters. But in part B, we have this plane of symmetry that goes right through the center of the molecule. What that means is that these are meso compounds. And if they're meso compounds, then by definition it's not chiral, and they are the same. All right, part C is a little bit harder to see what's going on because I've kind of rotated the molecule around to, make it a little more challenging. But you can undo what I did, which would be to rotate this molecule this way. And so if I rotate it back the other direction, now it looks more like the structure on the left. And what do we see if we do that? Well, we can see this stereocenter is the same. This one's the same. The third one is the same. But the fourth one has been inverted. And remember, if we change one stereocenter but not all of the stereocenters, that's when we have diastereomers. There is another way that you could go about this problem. And the other way that you could go about it is you could assign R and S for each center and see how many of them are the same and how many of them are different. Remembering that if they're all the same, then you've got the same compound. If they're all different, you have enantiomers, and if only some of them are different, you've got diastereomers. All right, part D, a little bit easier again. we've only got one chiral center. It's been inverted, and that means these are enantiomers. Part E, again, the key in Part E is very much like one of the previous questions. If we draw a line like that, you can see that these molecules are symmetric. We can see it on this side as well. That again makes these examples of meso compounds, and therefore they're not chiral and they're the same. In F, we've inverted this stereocenter. It's become the opposite. But our other stereocenter has stayed the same. Since we've kept one the same and changed the other one, that makes these diastereomers. In G, again, we have that internal plane of symmetry. So those are the same. Part H, there's no chirality to worry about at all. In fact, what we did was we actually took this OH and moved it. So these are what we would call constitutional isomers. Same chemical formula, different connectivity. In part I, we've changed one stereocenter, but not the other. That makes them diastereomers. Part J, these are just the same. They're actually resonance structures of each other. In K, again, we have this internal plane of symmetry, which makes them the same. And in part L, well, in part L, there's no chiral center. The center that looks like it might be chiral is that one, but there's two identical substituents, two CH3s, so it's not chiral, and they have to be the same.